we don't need that applet, the simulation applet, because I feel like we might understand, and you tell me if I'm wrong, I feel like we might understand what it was that we were doing the other day, right? Why we had I do want to start. Let's see. The results that we had. Too much brain width for my computer apparently. So okay, so we stopped, took a break last time when we were talking about estimating or hypothesis testing for the population, right? And we were doing it based on proportions. My notes over that particular section. We were doing it on proportions. We stopped at the end of class because we had kind of run out of time. We stopped at the end of class where we were stating our conclusions for that hypothesis, correct? So those were the notes that we were taking last time. And we had stopped here. And we kind of got into just how to state the conclusions, and we were talking about strength of evidence. Now, one of the things that I put on your paper there says, when observed results are unlikely under the assumption that the null hypothesis is true, that's when we state that the result is statistically significant. Now, if you look at studies, if you hear studies, a lot of times you will hear that phrase that something would be statistically significant. And what they're talking about is the fact that their results were unlikely given the null hypothesis is true. In other words, the p-value when they ran their test was small. Okay, do we all remember what the p-value was? What was the p-value? I put it on your notes like 4 times. Tell me what it was. I would have to go back and remind myself. So look back over that. What is the p-value?
Is it 0.10?
Not the value of it. I guess I should have stated, what does the p-value mean? Tell me what the interpretation of the p-value is. That's what I put. I kept repeating it in your notes, right? What's the p-value mean?
Probability of getting a result that is either the same or more less extreme than the actual observation.
That's right. It's the probability or likelihood of getting the sample results or more or extreme, right? If the null hypothesis is true. So when we say something like it is significantly significant, in other words, we're looking for that probability of getting that sample result. If it's an unlikely result or if it's an unlikely event to have happened, then the p-value would be small because the p-value is simply the probability of getting our sample result or more or less, right? That probability would be small, therefore it would be unlikely, right? It would be unusual for the null to be true in that particular case. That's what they mean when they're talking about statistically significant. Okay, so we kind of had our brain going with where we're talking about what we were talking about from the last class. Let's look at this particular example right here. This one, and it's going to be done in 2 parts. It says, and I'm going to change this. I want us to change this sample to be 248. That'll be a little bit clearer. All right. In a study conducted by Hill and Barton in the Nature journal that to investigate whether Olympic athletes in a certain uniform color have an advantage over their competitors. They noticed that competitors in the combat sports of boxing, taekwondo, Greco-Roman wrestling, and freestyle wrestling are randomly assigned red or blue uniforms. And for each match in 2004 Olympics, they reported the uniform color of the winner. Out of 457 matches, they found that the competitors wearing red won 248 times, whereas those wearing blue won 209. Do competitors wearing red have an advantage over blue? How many of y'all have ever heard that if you drive a certain color car, you're more likely to get pulled over for speeding? Anybody ever heard that? What color is it? Red, right? Y'all ever heard that? Okay, this is a similar concept right here. Okay, do players wearing red win more often? That's what they want to look at right here. All right, so let's go through and kind of summarize some of our information, right? This is how we're kind of setting up to understand our test. What is the variable that we are interested in here? What is the, what is changing? What is the variable that we're interested in, I guess? Who wins? All right, so we are interested in those that are wearing red winning, right? So red uniform winning. Is that a categorical or a quantitative variable? Right, it's categorical, or we would say qualitative, right? All right, so we have a qualitative variable because this answer is just, did you win or not wearing red? Yes or no? Now, what do you suppose if I were to flip a coin, right? And the coin heads represents red, tails represents blue. What do you think the chance of winning if I wore a red would be? A 50-50 chance, right? If it's evenly weighted, if you have an equally likely chance of winning wearing red or blue, then we would say that that's a 50-50 chance, right? That the likelihood of you winning if you wear red would be 50%. That's what we're going to assume. This is our population's parameter, that P would have to be equal to 0.5, right? If it is truly an equal chance of winning, if you wear red or blue, we're going to assume that's true. Then the population's parameter has to be 0.5. What is our statistic? What does the statistic describe again? Statistics describe what? The population or the sample? Okay. So what is the statistic that we're looking for here? What is the statistic that was given, I should say?
248 over 457.
All right, so that's the proportion of players who won wearing red, correct? That's the proportion of players who won wearing red. Say that 10 times fast. What variable do we assign our statistic?
Yeah.
P hat. I'm going to type P hat because I don't have the symbol readily available. P hat represents our sample statistic of 248 out of 457 matches. Those are the ones who won. Or in other words, when they looked at this competition, right, they found that approximately 54% of the matches had winners wearing red. Correct? Okay. Now, what do the researchers want to show?
If the competitors wearing red have an advantage over the ones wearing blue.
Okay, so is red more likely to win? Is that what they're showing? Yeah, okay. It helps to identify what the question is so that you can now go in and set up your null and alternative hypotheses. All right? So our null hypothesis is going to be something like maybe the probability that wearing red wins is 50%, right? Our null hypothesis is always about the population's parameter. Do you remember that? Okay. And the population parameter is that it's really just a flip of a coin. So symbolically, it would look like H sub 0, pretend that's a sub 0. H sub 0 would be P is equal to 0.5. The alternative hypothesis then is that the probability that wearing red wins what?
Is greater.
Is more than. Is more than, is greater than. What? Is more than 50%, right? So in other words, the alternative says P has to be greater than 0.5, right? Okay. So we have our parameter in our statistic identified. We have a research question identified, which helps us understand how to write now the null and the alternative hypotheses. We're ready because we have all of this data, we have all the information. We're now ready to go in and run the test using StatCrunch. So we're not going to simulate it. We're just going to jump to the to the technology, and I can do that by going to what screen in StatCrunch. Okay, y'all have StatCrunch open, I'm sure, right? Okay. Trying to get there fast. Where do we want to go? Where do I go to run a hypothesis test? No, I don't want to use that anymore. Oh, so I'm glad you said that. No more on that one. That's just to get us to understand how that probability is coming out. We're going to just dive straight in and say, okay, as long as I understand what the p-value it means, I'm going to move forward and I'm going to use technology. I'm going to use StatCrunch to do the rest. Where do we go to run our hypothesis test?
Portion stats. One sample with summary.
Right. I'm going to go to the same place I ran the confidence interval, right? It's exactly the same location. The number of successes. What's our number of successes? 248 out of how many observations? Good. Our test here is that P is equal to 0.5, correct? All right, but we do need to change our alternative to be more than, right? That's the only symbol I need to change in here. And I'm going to hit compute. All right, now we have this information here. I want everybody to make sure that you write down our p-value. Okay, so the p-value ends up being 0.0341. In other words, we'll call it 100 different repetitions of this scenario, right? In 100 different repetitions of this scenario, we would only expect about 3 out of 100 to have a result of 54% wearing red or more. Okay? Is it an unusual thing to have happen? Is it unusual for them to get a sample at this value or more? Yes, it is. Why?
That's less than 5%.
correct, and we were using, by the way, we were using our level of significance, we did need to see that. The level of significance was listed at 0.05. So that was what we were balancing it at, or basing it on. Remember that when we are looking at our test, we are saying, how does the p-value relate to the level of significance? That's the test, right? That's the way we're running it. Our p-value of 0.0341 is less than 0.05. So what conclusion do we make? You have the paper right there, right? You have your notes from last time. Based on this, based on the unlikelihood of getting a test result at this value or more, what conclusion do we make about the null hypothesis? What does your note say?
There is moderate evidence against the hypothesis.
So we're gonna reject the null, right? We're gonna reject the null, exactly. When the p-value is less than the level of significance, we reject the null because we are claiming that it is, the test is showing us that it's very unusual for us to have a sample like this if the null were really true. If it really was only a flip of a coin, if you had equally likely chance of winning if you were red or blue, then I would not have been able to get these results, is what it's saying, okay? Now to state it, we would say that there is, remember the fill in the blank I gave you at the front, right? Or just before class ended. There is sufficient evidence to suggest that, okay, I can't type all of that. Competitors wearing red have an advantage over those wearing blue. Could have also said there is sufficient evidence to suggest that the probability of wearing red wins more than 50%. That's a restatement of the alternative, correct? Yeah? It's also one of the reasons why it's helpful for you to write your null and alternative hypotheses in words. That way, when you make your conclusion, and your conclusion is in words, you have something to go off of, right? Okay? All right, so I can't type really fast. All right, the next question there says, do we all understand, by the way, this conclusion here? Okay, what type of a test is this? Two-tail or right tail or left tail?
Right.
It's a right tail. I had to look in my direction. Yeah, it's a right tail, right? Go back and look at your alternative inequality. Look at your alternative statement, right? P is pointing to the right. Our inequality, I mean, is pointing to the right. That means it's a right tail. Okay? Which is what we should have on the top, right? Going back and checking. Yep, right tail. And center. See that? Okay. So just look for the direction that the inequality symbol is pointing, and it helps you to see what the type of test is. This next question is going to come back and look at this scenario one more time, but we're going to look at it in a different way. All right. So in this particular case, it says, suppose that researchers do not necessarily think that red wins more often, but they don't really know that blue wins more often. In other words, they don't know. I don't know who wins more or less, right? So we want to know whether one color would win more often than another. We want to restate our null and test it again with the same level of significance. So what we're looking at here, I'm just going to pull this information down. What we're looking at here is the probability of winning wearing red is still going to stay the same for the population. We still don't know. I mean, we're assuming that it's going to be a flip of a coin. What happens in this particular statement in question 5 is, okay, they don't really know whether red wins more often or not. So that becomes a statement of not equals. I'm going to just put not equal. So if we're thinking about our tests from up here, right? If we're thinking about our tests that we were looking at, this becomes a two-tailed test. So a two-tailed test is where we have this statement of not equal, okay? Generally, when we are looking at a two-tailed test, is we are trying to find something that would not be the same. It would be something that is not equal. If we don't know, right? If we have no prior information about the test, you generally, or if you have no prior conclusion or guess, I would say, for your research question, then you typically use a two-tailed test. All right? Okay, so if we're running a two-tailed test here, a test of not equal, we're going to go back to our StatCrunch, and all I need to do is change the inequality symbol here, because everything else stayed the same. We're just trying to see what happens when I do that. So what is your p-value now?
0.0681.
0.0681, that's right. Okay, so what would we say here based on a level of significance of 0.05? Would we reject the null, or would we fail to reject the null?
Fail to reject,
Yes, and why?
because it's more than the sequence.
So the p-value of 0.06 is more than 0.05. 0.06 is more than 0.05. And so therefore, the conclusion, so since our p-value is more than 0.05, we fail to reject the null. That's what we were saying last time. In other words, there is not sufficient evidence to suggest players wearing red win more than 50% of the time. Now, we had, and I'll just write this here in the center, the p-value for a single tail was 0.0, we'll just call it 0.03, correct? For our right tail test. And the p-value that we just calculated on a two tail is 0.06, roughly, right? All right, you see that? So what do we see happening here? What is happening to the p-value? What happened here? Tell me how those numbers are related. The p-value on the two tail is what? Twice as much as the p-value on the single tail? Yes? Okay, so what's happening is, remember that on a two tail, we are taking, this is kind of an example of what was going on here. This is that simulation, by the way. But remember that if we kept our level of significance at 5% on a single tail, that all 5% has to come entirely in the tail, right? It has to happen entirely in the tail. So we're kind of testing against that tail right there. In a two-tail, we take that 5%, that level of significance of 5%, and now we split it between both tails. So we have both tails to now consider. When you don't know, right? If you don't know, and typically you don't have an information about a claim, maybe. If you don't know, then you are in essence making it harder to reject the null, right? Because the higher the p-value, when we have a larger p-value, we don't reject the null, right? We fail to reject the null. Okay. And what happens with a two-tail is that it will be doubling your p-value as compared to a single tail. Because the p-value for a two-sided test is about twice as large as that for a one, it provides less evidence against the null. All right. So it's it becomes a little bit harder to reject the null, which is fine if you didn't have any information contrary to that, right? Yeah? Okay, so that's our proportion hypothesis testing. Let's move on and let's talk now about our population mean, which is the second set of notes that I gave you there, okay? But before we get into running the test for our mean, which is going to be the same exact process as we did in the other one, let's kind of go back for a minute and talk about what happens if you make the wrong conclusion. Okay, so in this particular case, what we're going to talk about is we know that we make a conclusion based on our test of significance. Hopefully we made the correct conclusion, but maybe we didn't make the correct conclusion. What happens? What is the result of not making that correct conclusion? So what I've done here is kind of tried to explain a little bit about our p-value versus the level of significance. Now we have four results that can happen. Okay, we have four conclusions that could be made. If the p-value if we found the p-value was really, really small, okay, then we would conclude against the null, right? We would reject the null. When the p-value is small, we reject the null. And if that was the conclusion we made, that would be a correct conclusion. Number two says, okay, well, if our p-value is large, we fail to reject the null, so we keep the null. And if that was the conclusion that we made, again, that's a correct conclusion, right? We have these two outcomes we can have. Now, number three says, okay, well, if we rejected the null when the null was true, if we threw the null out when in fact the null was actually true, that's an error. That's the wrong conclusion, right? You concluded in the wrong way. And then in the other one, we have, if we fail to reject the null, we fail to reject the null because we throw out the alternative, but the null really isn't true. That's the other type of error we can have. There's four conclusions that can be made from a hypothesis test. Two of them would be correct and two of them would be incorrect. Okay? Okay, so what I want to talk about is, I want to come down and I'm actually going to skip. I'll let you go back and look at the box that I made in there for you. And actually I've got it right there. So I'm going to use this example to help explain what happens with when we make the conclusion. So I'm going to use this in the context of a jury trial. The other example that I gave you, where it was previous to this, that was an example. And if you want to write this down, it might be helpful. Yeah. So if you were to look right back up here on the jury trial, on the this one right here, okay, the one that I'm skipping, I would maybe write down that this idea, because you can make this little box right here for all different types of scenarios. But this scenario that is showing here is how many of y'all have heard about when you do a test, like a false positive on a test? COVID is one of them, right? Okay. And this scenario right here is talking about that scenario, right? What happens? What is the null? What is the alternative? What are the outcomes? So after we go over the jury trial, come back and maybe look at this and see if you can understand it. But I will tell you, maybe you want to write down that the null hypothesis for this box right here is, I did it on a pregnancy test. I thought that was kind of an interesting one. You can absolutely talk about COVID testing. But if the null hypothesis is that you are not pregnant, you're assuming that's true. The null hypothesis is you're not pregnant, and the alternative would be that you are pregnant. And these are the scenarios that can happen. Remember, you have 2 correct ones and you have 2 false ones. I'm not going to go over it right now. I'm going to skip down and I'm going to do the jury one. But if you want to come back and look at that one, it's kind of an interesting one. I know we have people in here that are in the medical field. So it's a good one to look at. But I kind of want to go over the jury one because that seems to resonate a little bit more with my students yesterday. So I'm going to start with that one instead. All right. So what we have here, and I left it blank so that you could actively fill it in as we're talking about it. If we want to discuss these errors, let's think of it in terms of the jury system. Remember that the null hypothesis in our jury system is that you are innocent. You are assumed innocent until proven guilty, correct? So the null is that you are innocent. Therefore, the alternative has to be that you're guilty. The null is that you're innocent, and I want everybody, before you start filling all of that in, let's talk about the correct decisions that can be made, all right? So if the jury comes back and finds the defendant guilty, when he's guilty, he or she is guilty, then that would be the correct decision. You would reject the null because you're keeping the alternative, right? So when the jury finds that the defendant is guilty, when in fact that is the reality that he is guilty, that would be a correct decision. When the jury comes back and finds the defendant not guilty, when he's not guilty, that again would be a correct decision. If they find him not guilty when he's innocent, then that would be a correct decision. Okay. And notice how when we state the conclusion for guilt, right, when the jury comes back, they don't say, we the jury find the defendant innocent. Do they ever say that? No. All the television shows I watch, they never say that, right? So what do they say instead?
Not
According
guilty.
to television, right? I'm assuming it happened. That he's not guilty, right? They always state the conclusion in terms of the alternative. Okay. Now, let's look at that type 1 error up there. A type 1 error says that you are incorrectly rejecting the null. You incorrectly reject the null when the null is true. So the jury finds the defendant guilty when he's innocent. A type 1 error, in terms of the jury system, a type 1 error is that the innocent man went to jail, right? He was innocent, but we rejected that and we find him guilty. So that's a type 1 error. The innocent man went to jail. And therefore, the type 2 error, because there's 2 that could occur, is that the jury, a type 2 error says you are going to fail to reject when the null is false. If the null is false, then the person would be guilty, but you fail to reject the null. In other words, you keep the null. In other words, the jury finds the defendant not guilty, so the guilty went free. Type 1 error is the innocent man went to jail. Type 2 error is that the guilty go free. And it's always helpful to keep coming back, highlight what the two type of errors mean. Type 1 error says you incorrectly reject the null when the null is true. Type 2 error says you fail to reject the null when the null is false. Remember, I gave you these notes because there's a lot of information on them, all right? Highlight, circle, whatever, but go back and refer to them. So a type 1 error in terms of the judicial system says that the innocent man went to jail, and type 2 is that the guilty go free. Now, you'll see, and I'll just hit it right here because I think it's kind of important, that these two errors, a type 1 error, which we call alpha, notice that symbol right there, alpha, and then a type 2 error is called beta, that's a capital B for beta. And where do we see the alpha? Where do we keep seeing it? That's our what? That's our level of significance. So if you look back on your papers from the other day, because I think you still have them out, flip over to, I think it's the second or third page, where it talks about the procedure for running a hypothesis test. And I think it's question number, or procedure 4. Select or identify the level of significance based on the seriousness of making a type 1 error. Does everybody see that? And I told you yesterday or the other day that we would kind of understand that by today. So in the middle of that page, you should see that information. That type 1 error is talking about this alpha that we see up here. If we know that 4 conclusions can come out of a hypothesis test, 2 of them correct, 2 of them not correct, our level of significance is chosen on how serious is it going to be if I make a type 1 error? How serious is it going to be if I incorrectly reject the null when the null was in fact true? That's what you're basing this on, okay? And what we see is, if we're talking about these 2 errors, is that the errors are actually inversely related to each other. So what does that mean? Again, thinking about the judicial system. Let's say that we're really concerned about the innocent man going to jail, right? Who wouldn't be? We want to maybe make it more difficult to accidentally send an innocent man to jail. So if that's the case, then what I might inadvertently do is, if I make it harder to send an innocent man to jail, then we might have, so if I make it harder, like less innocent people are going to jail, then the guilty people might be more likely to go free. More guilty people might end up going free because I made it harder to prosecute somebody who was actually innocent. They're inversely related. And the thing that it's the opposite way too. If I make it more difficult to send to let someone who's guilty go free, if I make it more difficult to let somebody who's guilty go free, then I have made it right. I'm going to increase the number of innocent people that I accidentally send to jail. See how they're inversely related to each other? Type 1 and type 2 errors are inversely related. You decide your level of significance based on incorrectly rejecting the null, understanding that you are going to inversely increase or decrease the opposite error, okay? So they're related in that way. All right, let's look at that next example 2 on hypodermic needles. Or actually, let's go back one. I take it back. Let's go back one. So this is the example previous to your jury one. And it's an application of what we were just talking about. Let's suppose that the average amount of sleep for MCC students was studied last night. The null hypothesis that we have in this test is going to be that MCC students slept an average of 8 hours last night. That's our null. Okay? The alternative would then be that they slept less than 8 hours last night, right? Or no hours last night, okay, if that's the case. So we have these two null these two questions, right? We have our null and our alternative. And let's just pretend we've run this test. And let's say that I asked both of my statistics classes, and I sampled them. And I found out from my sample, okay, I ran the test, and I found out that based on my sample, the p-value from my test ended up being 0, right? Like it was really small. That's pretty small, right? So the likelihood of me getting results at or more, right, of whatever I got was highly unlikely. Well, the actual conclusion, the correct conclusion based on the p-value, this in black is the correct conclusion based on that p-value is that we have strong evidence that MCC students slept less than 8 hours last night, right? The p-value is less than any of those levels of significance, but still it's really small. If the p-value is really small, we reject the null and keep the alternative. So I would correctly conclude for the alternative that there's evidence to show that they slept less than 8 hours last night. That's the correct conclusion. If we make a type 1 error, type 1 error, remember, is incorrectly rejecting the null when the null is true. Or in other words, concluding for the alternative when the null is true. So if my conclusion instead had been, we conclude that MCC students slept less than 8 hours last night, that's the alternative, when in fact they didn't. That would be a type 1 error. Okay, all I'm doing in this example is trying to point out, you're going to have to do this on your homework as well, what would the conclusion look like had you made a type 1 or a type 2 error? Type 2 error says you fail to reject the null when the null is false, or you conclude in favor of the null when the null is false. Okay, you might want to add those statements to what whatever you've got. Type 1 error is concluding for the alternative when the null is true. Type 2 error is conclude in favor of the null when it's really false. So that would look something like, we conclude that MCC students slept 8 hours when in fact they did not. Okay. I'll give you just a second to make sure you have that written down. And then I'm going to go into the other question for the hypodermic needles. Okay, we ready to move on? Yeah? All right. So let's try that out with our hypodermic needles, okay? So you all have the hypodermic needle problem sitting there on your paper. It says, consider a manufacturing process that is producing hypodermic needles that will be used for blood donations. These needles have to have a diameter of 1.65 millimeters, too big and they would hurt the donor, too small and they would rupture the red blood cells. Thus, the manufacturing process would have to be closely monitored to detect any significant departures from the desired diameter. During every shift, quality control personnel take a sample of several needles and measure their diameters. And if they discover a problem, they stop the manufacturing process. So, I think I left a blank for you right there. Let's determine before we move on, what's the population and the parameter here?
1.65.
That would be the parameter, that's right. And it's talking about all needle diameters, right? Of whatever this is, right? Okay. What variable, because I'm changing now here, what variable are you gonna put in front of that 1.65 millimeters? So 1.65 is the variable, correct? That's what we're interested in. What type of variable is it? Is it quantitative or qualitative?
Quantitative.
It's quantitative, right? Because it would be an average size. That's what we're looking at. Therefore, what letter will I use to represent the population parameter in this case?
X.
Population. Mu. Mu. U, right? U. Mu. So how would I come up with a null hypothesis? What's the research question? Ellie, are you eating candy corns or pretzels?
I'm sorry, I haven't eaten since.
That's fine, I don't care that you're having
That's
them.
fine.
I was just like, oh, that looks good. What's the research question here? What are they kind of wondering about? What do they want to make sure is happening?
That the needles are equal to 1.65.
All right, that the average needle size, we're gonna say that, right? The average needle size is 1.65. Okay? So that's how we get to our null and our alternative. So here, I have the long run average needle diameter is 1.65 millimeters, or in other words, that the mu is equal to 1.65. And the alternative would have to be that it's different from 1.65. What type of tail is that? What type of test is that? Two tail, right? Because it's different. We're not saying it's more, we're not saying it's less, we're saying it's different. Very good. Now, let's see what would it look like if we made a type 1 error. And we want to state what the consequence would be. Remember, a type 1 error is when we incorrectly reject the null when the null is really true. Do you all have the null written down? And do you have the alternative written down? Okay. The statement is about the alternative. The conclusion is based on the null. Feels like it's a big circle when we do these. So a type 1 error says we conclude for the alternative when the null is true. What would that look like? What would your conclusion look like if you made that type 1 error? Tell me verbally. Conclude for the alternative when the null is true. What's the alternative say?
That the average needle diameter is different than 1.65.
All right, so if we said that we have evidence that the long run average needle diameter is different, when in fact it's actually 1.65, right? What we're saying in a type 1 error is that it would be different when actually it's not. And the consequences of that, if you look back at the sentence in the paragraph or the lead up to this, it said, okay, well, during every shift, quality control takes a sample and measure their diameters. If they discover a problem, they stop the manufacturing process. So if they incorrectly said that it was not meeting that standard, right? If they incorrectly found the alternative, they would have stopped production for probably no reason. You see the consequences of that happening when in fact it's not? Okay, well, let's think about what a type 2 error then means. Remember that a type 2 error says that you incorrectly, you fail to reject, the null. You fail to reject the null when the null is false. You fail to reject the null when the null is false. You conclude in favor of the null when it's really false. What type of conclusion would we make here for type 2?
We conclude the average needle size is equal to 1.65 when in fact it's not.
Put it in terms of the alternative. Remember, we either have sufficient evidence or not sufficient evidence. Let's put it that way instead. So if we fail to reject the null, right? If we fail to, we're keeping the null then, right? If we fail to reject the null, then we keep the null. So we don't have sufficient evidence to conclude in the alternative, is what that's saying, right? Okay. So we might say that we have insufficient evidence or we don't have evidence that the long run average needle diameter is different from 1.65, right? That's the alternative. When in fact it really is. There's our type 2 error right there. We don't have evidence that the long run average needle diameter is different from that when it actually is. So that consequence would be a wrong diameter being sold. Which could be bad for business. Okay? All right. So what I want you to do, and I want to make sure that you have written down those two ways that we can describe a type 1 error. The more ways you can describe it, I think the better in your interpretation, right? First, type 1 errors say that we incorrectly reject the null when the null is true. Or in other words, we conclude for the alternative when the null is true, right? That's a type 1 error. Type 2 error says that you fail to reject the null when the null is false. Or you conclude in favor of the null when it's really false. And just restating it two different ways, okay? So having said that, there are three problems for you right there. Type 1 and 2 errors. First, what I want you to do is determine what your null and alternative hypotheses are in symbols. All right. You have three of them there. Each one of them is doing a different parameter. And then I want you to just briefly write down the phrase or what it means to make both your type 1 and type 2 errors on those three. Okay? Based on the conclusion. All right, so you have those three problems there. I was letting everybody write this down. So example number 3 says type 1 and 2 errors. I want you to see if you can answer A, B, and C and describe what it would mean to make both a type 1 and a type 2 error. I'm just going to give you a few minutes. You're welcome to lean over or talk about it with somebody else if you would like. Let's just take a few minutes before we move on. Thank you. We'll start by writing down what your parameter is for those questions, as well as the null and the alternative. Okay, how you doing? Did you get them done? You got it, you got them all done? Still working on them? Did you answer? Still didn't answer. How many of y'all are done? Okay. got about another minute to finish those up, and then we'll go over the answers together, all right? All right, let's look at the results. So the first question there says, federal law requires that a jar of peanut butter is labeled as containing 32 ounces must contain at least 32 ounces. Consumer advocates feel that a certain peanut butter manufacturer is shorting their customers by filling their jars. So in this case, this is about a mean, because it's measuring quantitative information. The null hypothesis says that it's equal, mu is equal to 32 ounces. And the claim, the alternative then is that it's less than, okay? So to make a type 1 error where we would conclude for the alternative when the null is really true, in other words, we reject the null when it was in fact true, is that we would conclude that the jar has less than 32 ounces when in fact it doesn't. That's the conclusion. That's a type 1 error. Type 2 error says that you failed to reject the null when the null is false. So if we concluded that it was filled to 32 ounces when they didn't. Remember that what we reject or what we keep, we always state it based on the alternative, right? Did y'all ever hear about that lawsuit that somebody and some woman brought against Starbucks? I think it was Starbucks on their iced coffee or something like that. And she brought, I think it was Starbucks or McDonald's, it was somebody who served that. And she got a lawsuit against them because she didn't think that she was getting the right amount of, she thought she was being shorted her drink. Did you ever hear about that? I heard about it one day on the way to school, and since I teach statistics now, I was like, oh, wait, what was that? Well, the claim was that she wasn't getting the right amount. So let's say her cup was 32 ounces. She didn't feel like she was getting 32 ounces of her iced coffee. What do you think happened? So they put like ice in there, right? So, that affects the volume of the container when you have ice in there. It's kind of interesting. I think that her lawsuit did not turn out well. Next one, in 2014, the standard deviation of SAT scores on the critical reading test for all students taking the exam was 112. So this is a statement about standard deviations, sigma. So the null hypothesis says that it's equal to 112, and they think that it has decreased. So we would say that sigma is less than 112. Those are the null and the alternative. So the type 1 error is that we would reject the null. So we would conclude that the standard deviation is less than 112 when in fact it wasn't. Or type 2, if we fail to reject the null, so we would conclude that the standard deviation is equal to 112 when it's not. Okay, and then the last one, we have our adults volunteering. the proportion of adults who volunteer, so in that particular case, that is about a P. So our null hypothesis says that P is equal to 0.62, and the alternative is that it's not equal to 0.62 because they said that it is different. So type 1 is to conclude that the proportion is not equal when in fact it is. Type 2 is concluding that it was still 62 when in fact it was not. All right, those are our conclusions. So under that is really just me talking one more time about the probability of making those errors, or how they are related. Just remember that alpha, we've already defined our level of significance as the most common levels of significance would be that 0.1, 0.05, or 0.01. 10%, 5%, or 1%, right? Those are the most common levels of significance. Okay. Now, what I would like to look at is, I'm going to skip down and we're going to talk about hypothesis testing for a population mean, because we only have about 10 minutes left in class. All right, how do I run a test for a population mean? The same way that I ran it for a confidence interval. Okay, remember when we started talking about means, we had something come up with our confidence intervals on a mean that said we had to start using the t-test. Remember that? Yeah? Okay, and that we used our t-test because we didn't know sigma. We didn't know the population's standard deviation, correct? That same criteria is how we decide what type of hypothesis test we run. We are going to specifically only be running t-tests here in class. So we're going to follow the same information. All right. This is a rehash of what we've already been given. The fact that our test statistic is based on a t-score now instead of a z-score. Okay. That's if I were to ask you to calculate the test statistic. I'm not really going to do that. We know that we have to meet certain requirements, whether we're doing a proportion test or a t-test. Those requirements are simply saying that the distribution comes from a normal distribution, right? Okay. And we are just putting up here our notations that we have n for a sample size, x bar for a sample mean, and mu is the population mean. To run the test, you go to StatCrunch. Okay, that's pretty much it. You go to StatCrunch. Okay, so let's look at that next example that we see down there. It says that commute times in California wanted to be studied. According to Pew Research, in 2012, the average commute time to work in California is 27.5 minutes. To investigate whether a different average is true for a small city that she lives in, a California high school student surveyed 45 people she knew and found that the average commute time for this sample was 24.33 minutes with a standard deviation of 9.53. Now, before we go on, let's think about a couple of things, okay? First of all, what's the parameter here? 27.5, that is the average commute time for the population, correct? What symbol will I assign it? What type of variable are we looking at here? A proportion, a standard deviation, or a mean?
A mean.
So what symbol am I going to assign to 27.5 minutes?
Mu.
Mu, very good. So the population's parameter says that mu is equal to 27.5 minutes. What else do we know in that paragraph? What's 45?
The sample size.
All right, so in a sample of 45 people, what's 24.33?
The sample mean.
The sample mean, and what variable do I assign it?
X bar.
Good. X bar is 24.33. And what is 9.53 of what? It's the standard deviation of what? The sample or the population? So it's little s. Sample standard deviation is 9.53. Okay. So what is the research question that this girl wanted to know?
The average commute time to California.
That's what we assume to be true. What does she want to show?
A different average for a small.
That it's different. Do you see the word different up there in there? Right? Okay. So the research question is about that the commute time is different. If it's a different average, right? So the null hypothesis, right? Let's come up with our null hypothesis. If I were to write the null hypothesis, it would look like what? The average commute time in a California city. The null hypothesis and the alternative are always about the sample or the population. Okay, so if it's about the population, what are we saying that the average commute time in California is? So we're saying that it is 27.5 minutes, right? Or in other words, that mu is equal to 27.5 is the null hypothesis in symbols. And so what is the alternative hypothesis? Give it to me in words and I'll try to type as fast as you speak. Start you out, duh.
The average commute time in a California city is different than 27.5.
Is different than 27.5. Okay, and what does that symbolic representation look like? Tell me what it would look like.
Mu does not equal 27.
Mu does not equal 27.5, correct? Okay, so we have everything that we need to know and we can move on to the test. So if I go to StatCrunch, remember in StatCrunch, we're gonna run a t-test for a mean. A t-test for a mean. One sample with summary, and then everything that we wrote down out of that paragraph should be there for us to fill in. We know that the sample mean was given to us at 24.33. The sample standard deviation was 9.53. The sample size was 45. And we're saying that the claim is that the average commute time was 27.5 minutes. She thinks it's something different. The two-tailed test, right? Right, hit compute. And well, we don't need to know that just yet. So our p-value is 0.0308, correct? Everybody get 0.0308? Good. All right. Now, because 0.03 is less than the level of significance that I stated up there, I didn't state it in there. When it's not stated, it should be understood to be 0.05, right? Seems like I've only done 0.05. But the level of significance that we're thinking is 0.05. The p-value is less than 0.05, so we would reject the null, right? In other words, the likelihood of her getting a sample with an average commute time of 24.3 other than 24.3 only happened about 3 out of 100 times, right? Probability of that happening, so then we would reject the null, correct? If that's truly the null, if that's the true commute time for California, then you would expect different results from your sampling, wouldn't you? Okay, so if we reject the null, somebody tell me, how do I state this conclusion in words? You have a thing, right? You got a template. I'm rejecting the null. You got a template. How are you gonna use it? We reject the null, we're keeping the alternative, correct? We reject the null, we keep the alternative.
There is sufficient evidence to conclude that the average driving time in a California city is different than 27.5.
Exactly, right? Exactly. We would say that because that p-value is less than 0.05, that's our conclusion, right? Or that's how we're getting there. But yes, we have strong evidence, we have sufficient evidence, whatever I don't really care about that adjective, right? Or adverb. We have strong evidence that the average commute time in the California city is different than 27.5. This was a two-tailed test, and I just put that on there so that we would be reminded that when you're talking about a two-tailed test, that 5% is split between 2.5% and the tails, right? Okay, so the likelihood of us getting that is that. Now, I'm pretty much out of time, but I want to point out to you one quick thing. What was the sample size here in our test? What was the sample size again? 45. Remember, the central limit theorem is invoked on a mean as long as your sample is greater than 30, correct? So we don't have to do anything fancy here. We don't have to test the validity conditions because the central limit theorem was invoked. If you look at the very next question that I also have on your paper to do, it says that they're going to measure whether or not the weight of a quarter is the same or different or something like that. All right, that was what they wanted to know, the average weight of this quarter. And they ended up with a sample of only 18. Remember that if we're doing a mean, the validity conditions, the central limit theorem doesn't kick in until 30. I have a sample size less than that, and therefore that's usually why you get walked through having to verify the validity conditions, which is, we already talked about this in confidence intervals, right? The validity conditions have to be met by you doing a QQ plot and evaluating the box plot, okay? That's all that second question said. Feeling a little bit more comfortable? Okay, the testing of the proportion and the mean is the same. What really becomes just the practice is how do you make the conclusion? Okay, all right, so you do have a homework over these. There's really 3 sections. I just don't know if I'll try to make sure. I don't know if I combined 2 and I don't know if you have 2 or 3 sets of homework. Okay, y'all have a great weekend. Oh, next week we have a test over this material. All right, so Tuesday would be our time to actually be covering, to practice this material as well. Okay, all right, y'all have a nice weekend.